Okay, so I'll go over the first page rather quickly because these are sort of fundamental aspects of the language and notation of mathematics. I hope you can, or you know most of these already. Okay, so as a member of the mathematical community, which is global, and I expect you to be able to read and write and speak the language of mathematics, all right? So the language of mathematics is primarily that of sets, okay? Sets of numbers, sets of functions, and sets of this and that. So the most basic entity in all of mathematics is the empty set. Now, you know the notation for the empty set. It sort of looks like this. And it's a set with no elements. Sometimes you can just go ahead and write it like this. That's also the same thing. It's, you know, it doesn't seem to be anything important, but it turns out this is probably the most important and the most fundamental entity in all of mathematics. Okay, now you can't do a whole lot. It's sort of pointless, literally. And so we start to talk about numbers, which are, again, another big elements, not the whole thing, but certainly mathematics is based on some numbers at least. Okay, so the set of integers, right? So you have number 0, which is, doesn't mean nothing, right? It's the number 0, which is a point on the number line. You can have plus or minus 1, plus minus 2, plus minus 3. All of these are integers. Okay, now when you say integers, okay, you have actually, you know what, maybe I can go to number 3, the set of positive integers. These are sometimes called natural numbers. And you probably learned what a natural number is. These are numbers that are very natural. Okay. Now, notice here, these are all sets. So I'm using the set notation, which are these brackets, okay, in order to list the elements of these sets. And since all of these, well, both of these are infinite sets, I have to use these dots, right, ellipses, to tell you that the numbers will continue to go on forever. All right, the set of positive integers is the set 1, 2, 3, 4, and so on, and we denote it with a script n. This is sort of a bold and mathematical boldface n. And so the set of integers, positive integers, that's sometimes called the counting numbers, right? Well, the problem here is, of course, you can add any natural number with natural number, and the answer will be a natural number. Same thing for multiplication, but subtraction doesn't work that way. 2 minus 4 is what, right? You don't have the answer here, so you have to sort of either create or just assume the existence of negative numbers, and that's how we get to this part, right? So you have a set of natural numbers to start with, and then a set of integers. And then you have a problem with division. When you have 3 divided by 4, the answer is not in the natural numbers or in the set of integers. So we have to create a set of all rational numbers. This letter is R, but for the set of rational numbers, we use the letter Q to denote that set. So this is a little more difficult to write. We write this in the set builder notation, which is P over Q, where P and Q are integers. Okay. Now, I can write P and Q are integers. So they can be positive or negative. I was going to write something else here, but I guess I'll wait for a moment. P and Q are integers. And then there's one more very important restriction here, right? Everybody knows this? Yep, Q cannot be 0. We have all sorts of contradictions when you have a denominator equal to 0. And so don't write that, okay? You don't write anything like this or this, okay? Because these are, and even though these could mean something like, you know, the indeterminate forms that you learned in Calculus 2, these are what I consider bad words, okay? So you don't say these or write these in public. Okay, and these are the last time you will see me do this. Okay, all right. The set of real, so the problem with the set of rational numbers, okay, this is the set of all ratios, right? Ratios of integers. The problem is numbers like the square root of 2 is not even in there, even though this is everywhere, right? If you have a number line here, the rational numbers are everywhere. I mean, in between any number and any other number, you have, I mean, literally infinitely many rational numbers. But still, it doesn't cover the entire real line. So for the real line, you have all these irrational numbers. And so the set of all real numbers. Now, this is even harder to describe, and it's really difficult to define what the set of real numbers is. You can say it's all the points on the line. Okay, well, great, but what is a line? You know, and so it would require you probably in a few years, if you stick to your mathematical pathway, if you take a class in the 4-year university like real analysis, you will probably finally see the definition of the set of real numbers. There are a couple of them, but they are really rigorous and hard. Okay. You could also think of this as the set of all decimals. Because when I say decimals, I'm talking obviously about the ones that stop, you know, like 0.2, or the ones that continue on repeatedly, like 0.99999, and also the ones that are, you know, random or that seem to be random, like pi or e or square root of 2, and so forth. Right? All of these are non-rational, we call irrational numbers, but they are still points on the number line, and therefore they are real numbers. Okay, I know that you have. I know you have already seen these. You know, this kind of thing here. This is interval notation, and we'll be using these. All right. So the reason I'm going through this is because I want you to know, and we all want to understand, that these are some of the notation symbols that we are going to use in speaking and listening to mathematics. Okay, the plane. What is the plane? Okay, plane. We notice that plane is really the set of ordered pairs. Okay, so how do you describe the set of ordered pairs? Well, we use parentheses and x and y, where x and y are real numbers. Okay, we allow all reals, right? And so that's the way to write this. And of course, the way to visualize this is, you know, you have x, y, y plane. This is something you have seen ever since you took your first algebra class. The entire plane is, of course, the set of all of these points, okay? But algebraically, you can write it in this way. The three-dimensional space, because we have 3 dimensions, we write this as R with 3 as the exponent. And of course, this is the set of all triples. Where x, y, z are reals. We are probably the only people that who use the word real as a noun. You know, when I say a real, I mean a real number. When I say the reals, I'm talking about the set of all real numbers. Okay, so all right, now you say alpha is a real number. Alpha is, of course, a letter in the Greek alphabet. And so the way you write this is you can say alpha belongs to the set R, right? Or you can say alpha is a real number. I mean, that's what I did here and here. But in set theoretical notation, we can use this thing that looks like a upside down epsilon, or epsilon flipped the wrong way. But this means is an element of or belongs to the set. Okay, so we can rewrite this whole long English sentence in this concise mathematical notation. The interval, okay, so the next few are intervals. You know what this means, right? When you have these square brackets, this interval, this is a set of all, how do I write this? You can say it's a set of all reals, which is between 0 and 2, right? And including the both endpoints. And so you can also describe this using a graph, you know, 0 and 2. And you can say this is all the numbers in between 0 and 2, including the endpoints. All right, so that's the interval, the closed interval. And the word closed actually has a very significant and precise meaning. But for the purposes of this class, you can just say that the set is closed when the both, or I shouldn't say both, when the boundary points are included in the set. Okay, that's probably the best way to say that. The interval, 0 to infinity. Okay, so again, this is the set of all x, so that it's between 0 and infinity. Well, you don't have to write infinity. All you have to do is just that. Okay, and when you do this, my computer is actually lagging in time. It's a little slower. That's all you have to do. And of course, you don't have to specify the largest number because there is no maximum number here, right? And so because there's a bracket here, square bracket here, the number 0 is included, and then you can write the rest of it this way. Okay, now the other 2 or 3, and then we go into the second page. Go ahead and try to write similar statements for 11 and 12, okay? And then I'll come back on the second part of this video, okay? All right, so try to do that, and then I'll be right back.